Last chapter, cells and simple circuits. Now, we use electricity for almost all the appliances at home. Lights, television, music systems, and the computers all run on electricity. How electricity powers these devices is a whole different issue. We need to first understand what electricity is by looking at simple circuits. This is a simple electric circuit with a bulb and a battery. A circuit is a loop through which electric current can flow. Most people know that the bulb lights because electric current or simply electricity is flowing. But just what is electric current? In the previous chapter, we said that electrons in the outermost energy level of atoms are weakly attracted to the nucleus and easily get dislodged. These dislodged electrons are called free delocalized electrons. And so, if we look inside a copper wire, there are atoms and their electrons are dislodging and swapping between one atom and another. These electrons are moving from one atom to another in any direction. Now, if we make a closed circuit by connecting a battery to the copper wire, the battery supplies a force that pushes the electrons in one direction, usually from the negative terminal to the positive terminal of the battery or cell. And if we add a light bulb to the circuit, the electrons will flow through it and cause it to light. So inside the conducting wire, electrons are moving or traveling at high speeds in only one direction, and therefore there is a flow of charge. This flow of charge per unit time is called electric current. Electric current is the flow of electric charge in a conductor over a period of time. The symbol of current is I. Current is given by charge over time, that is Q over T, which gives the units of coulombs per second. This is called amperes. It is the SI unit of current, denoted as E. And so, if 360 coulombs of charge flow through a bulb for a period of 3 minutes, we can calculate the amount of current flowing through the bulb. Current is equal to charge over time. 360 coulombs over 180 seconds gives us 2 amperes. The amount of current flowing in a circuit is directly measured by a device called an ammeter. Next, we look at conventional circuit diagrams. Now, what we have seen is a simple electric circuit. However, electric circuits could have very many components, and as such, we do not draw the component images. Rather, we use conventional symbols for simplicity. This is the conventional symbol for a cell. A cell gives energy to electrons in a circuit. The thick, short line indicates the negative terminal, and the longer, thin line shows the positive terminal. This is a single cell. When you have more than one cell, then it's a battery. This symbol indicates a battery made up of 2 cells. So your torch has 2 cells and not 2 batteries. Conductors are represented by straight lines. This is a switch. It closes and opens a circuit. This is an open switch, so no current flows in this case. And this is a closed switch. A bulb or a lamp is drawn with a circle and a cross, as shown here. This is a fixed resistor. We will learn more about resistors in Form 3. But we can just mention it restricts the flow of current. This is a variable resistor. It simply means we can vary its resistance to the flow of current. It basically regulates the amount of current passing through a circuit. An ammeter is represented by a circle with letter A and two short conductors. It measures the amount of current in a circuit. A voltmeter looks like an ammeter, except the letter V is used instead of A. It measures the potential difference across a component. These and many more symbols are important, but there is no way to understand them. You will just have to memorize them. So, this is a complete diagram for a simple circuit. The conductors must be straight with no breaks. Corners are at right angles. Next, electromotive force and the potential difference. Now, we said that the battery drives the charges through the circuit. Let us now understand how that works. Imagine you have two containers filled with equal amounts of water, and they are both connected to each other by a pipe at the bottom. No matter how long the setup stands, the water will never move from one container to the other. But there is one way to make the water move from container 2 to container 1 without changing the amount of water in any of them. That is raising the height of container 2. In simple terms, the water flowed due to a difference in height. In the same way, electrons will flow when there is a difference of some sort. When a battery is connected, it acts as a pump, raising the electrons to a higher potential, and they flow to a lower potential region. This difference is called the potential difference of voltage. The higher the potential difference, the stronger the current in the circuit. When you hold a ball in your hand, it possesses potential energy. So when you drop it, this potential energy is gradually converted to kinetic energy. Just like the ball in your hand has high potential energy, a negative charge close to another negative charge has high potential energy. If left free, the charge will be repelled by the other negative charges and will move towards the positive charge, just like the ball will fall towards the ground. This is how a cell or a battery creates an electrical potential difference, by separating the positive and negative electric charges. The electrical potential difference is measured in volts and is also called voltage. When a battery is not conducting any current, the voltage across its terminals is called the electromotive force EMF, or the unloaded voltage. But when the cell is conducting, the voltage across its terminals is called the potential difference. This is what drives the current through the circuit. Potential difference is usually less than the EMF. The difference is known as the lost volts. And this is because when conducting, there is some amount of resistance in all electrical devices and components. When current flows, the voltage across the terminals of the battery is no longer the unloaded voltage. There is a voltage drop inside the battery due to internal resistance of the battery itself. Both the potential difference and EMF are measured by a voltmeter. Note that we measure current in the circuit and voltage across devices. So the ammeter is usually connected in series anywhere in the circuit, while the voltmeter is connected in parallel with the device whose voltage across the ends we want to measure. In this case, we are measuring the voltage across the bulb. Next, we look at series and parallel connections. We take two 1.5 volts electric cells. The region with the metal cap is the positive terminal of the cell, and the opposite side, the region with the flat base, is the negative terminal. We join the positive terminal of one cell to the negative terminal of the other using a tape. This is called a battery. A battery is simply a combination of two or more electric cells connected together. If the cells are connected with their opposite terminals in contact with each other, this is called a series combination. The cells are said to be connected in series. In everyday life, we call this single cell a battery, but in physics, a battery is a combination of more than one cell. We can connect more cells in this combination as long as the positive and negative terminals are connected together. Even if four are connected together, it will still be called one battery. So, what will be the voltage of a battery combination of two cells? If the cells are connected in series, then their voltages add up. This means that the voltage of this battery will be 1.5 plus 1.5 volts, the sum of these two voltages, which is equal to 3 volts. So this battery is twice as strong as one individual cell of the battery. Does that mean the battery will last twice as long? No. We need to understand that different devices require different voltages to function. The torch bulb requires a 3 volts battery to light up. This is why we use a series combination of cells in a torch. Even battery compartments in devices are designed for series combinations. When the cells are connected, even though the terminals are not in direct contact, this wire links the positive and negative terminals. When the positive terminals of battery cells are connected together, and similarly negative terminals of cells are connected together, then the cells are said to be connected in parallel. In parallel connections, the total voltage is equal to that of a single cell. Parallel connections are only done with cells of equal voltages, otherwise one will drain the others. The advantage of parallel connections is that the current supply is longer, but even then, parallel connections are very rare. We can also connect bulbs in series or parallel. When bulbs are lined up one after the other in a circuit like this one, it is a series circuit. The problem with a series circuit is that when one bulb blows out, it creates a gap in the circuit. This means all the others go out as well. Usually, we do not connect bulbs in series. We instead do a parallel circuit. Here, the wires that are connected to the bulbs run parallel to each other rather than having the bulbs in a row. It means one bulb can be removed without affecting the others because each has a complete path for electrons to flow. Now, let's talk about something that many people find confusing: conventional and actual electron flow. One of the most confusing things about the study of electricity is why current flows from the positive to the negative terminal, even though electron flow is from the negative to the positive terminal. Consider this dry cell on the screen. It has one positive and one negative terminal. The potential difference between the two terminals is due to the excess of electrons at the negative terminal compared to the positive terminal. If we connect a wire across these two terminals, the potential difference causes electric current to flow in the circuit. This current is nothing but the flow of electrons that come out of the negative terminal, move along the wires, and enter the cell by the positive terminal. However, back in the early days when scientists were still figuring out the basics of electricity, they did not know whether it was the protons or the electrons that were flowing. So they made an arbitrary decision that current was flowing from the positive to the negative terminal. This is the conventional current flow. However, this conventional current flow turned out to be wrong in the later years, because we now know that it is electrons that flow, and they flow from the negative to the positive terminal. Unfortunately, any formula that we use in the electricity studies is based on the mistake of conventional current flow. The good news is that the formulas are consistent simply because electric flow is in a loop. So mathematical calculations based on the conventional current flow works just perfectly. Next, we talk about conductors and insulators. It is common experience that some materials do and others do not conduct electricity, hence the terms conductors and non-conductors. Metals are good conductors, for example copper, silver and gold. These two are not often used because they are very expensive. If we look closely at the structure of copper, it has a positively charged structure of metal atoms surrounded by loosely held electrons. The loosely held electrons are free to move randomly in the metal, and once a battery or a source of voltage is applied, the electrons flow in one direction, generating electric current in the metal conductor. Some materials offer hardly any resistance to the flow of current or the movement of these electrons. Some non-metals like graphite, which is a form of carbon, or solutions of salts forming electrically charged ions will conduct electricity, but these have more resistance. They are poor conductors. Most solids, however, have tightly held electrons which are locked in chemical bonds, so they do not move around. Examples include solid salt, sulfur, polythene, and glass. These are non-conductors. They are used as insulators around conductors to prevent electric shock when the cable is touched. Next, sources of electricity. Now, there are 7 fundamental forms of electricity generation. All create an EMF or electromotive force. One of the most commonly used form of electricity generation is the electrochemical reaction. Substances such as acids dissolve in water to form charged particles called cations and anions. These types of solutions form the electrolyte of a cell. Metal rods immersed in electrolytes act as electrodes. The positive electrode is called the anode, and the negative electrode is called the cathode. These electrodes attract oppositely charged ions, resulting in flow of electrons. This is called a chemical cell. There are 2 types of chemical cells, primary and secondary. Primary cells cannot be renewed once the chemicals are depleted. A simple primary cell consists of 2 electrodes, one of copper and the other of zinc, dipped in a solution of dilute sulfuric acid in a glass vessel. On connecting the 2 electrodes externally with conductors, current flows from the copper to zinc outside the cell, and from zinc to copper in the solution. The action of the cell is explained in terms of motion of the charged ions. The dilute sulfuric acid exists in solution as hydrogen and sulfate ions. At the zinc electrode, zinc atoms get oxidized and go into solution as zinc ions and releasing 2 electrons. These electrons flow along the external circuit to the copper electrode, creating an electric current. At the surface of the copper electrode, the electrons combine with 2 hydrogen ions to form hydrogen gas. The gas bubbles accumulate around the copper electrode in what we call polarization. This creates resistance to current flow. Meanwhile, the zinc electrode is corroded by the acid in what we call local action. So polarization and local action are the main problems of these cells. Next is the Laclanche cell. In this cell, a carbon rod is placed in a porous pot containing a mixture of manganese 4 oxide or manganese dioxide and powdered carbon. The porous pot and the amalgamated zinc rod are placed in a glass jar containing saturated ammonium chloride solution. Ammonium chloride solution is the electrolyte, while carbon and zinc rods are the electrodes. Ammonium chloride splits into ammonium and chloride ions. The chloride ions move towards the zinc rod and transfer the electrons to the zinc rod, forming zinc chloride. The zinc rod contains negative charges due to the excess of electrons, so it becomes the cathode. On the other hand, the ammonium ions move to the carbon rod. The free ions of the carbon rod neutralize the ammonium ions, forming ammonia and hydrogen gas. As a result, the carbon rod attains a positive charge due to deficiency of electrons. It therefore becomes the anode or the positive electrode. The hydrogen gas is oxidized by manganese 4 oxide to form water, and polarization is prevented. If an external copper wire is connected to the electrodes, electrons move from the cathode to the anode, generating electricity. The EMF of the cell is 1.5 volts. Next, the dry cell. A cell is the simplest unit for making electricity. It generates electricity from chemical reactions. The anode is a graphite rod. The zinc container is the cathode, and the electrolyte is a moist jelly paste of ammonium chloride enclosed in the metal cylinder. A mixture of manganese dioxide and powdered carbon surround the graphite rod. The jelly is kept moist by sealing the top of the cell with a pitch. A cardboard washer is used to prevent the cathode and the anode from coming into contact. The zinc can is surrounded by an insulating thick paper covering. The positive terminal is a brass knob at the top, while the negative terminal is at the base. The reactions taking place inside are quite complex, but here are simplified ones. At the cathode, zinc is oxidized to release 2 electrons. These are collected by the graphite anode. At the graphite anode, reduction takes place. This flow of electrons produces electric current. The dry cell produces a voltage of 1.5. However, local effect is still a problem in this cell. The cell is not rechargeable. Secondary cells. The chemical processes that take place in secondary cells when generating current can be reversed by applying a direct current to the terminals. These cells are also called storage cells. Examples include the lead acid accumulators and the alkaline accumulators. We start with the lead acid accumulators. This is the battery that essentially stores electrical energy. A lead acid battery contains 6 cells, each of 2 volts. The cathodes are linked plates with grids filled with lead-2 oxide, while the anodes are linked plates filled with spongy lead separated by a separator plate. Dilute sulfuric acid is the electrolyte. This reacts with the 2 plates in a chemical process that creates electric current that powers the load connected outside. At the positive plate, sulfate ions react with lead to form lead-2 sulfate, while the hydrogen ions react with the oxygen in the lead-4 oxide to form water. At the cathode, lead reacts with sulfuric acid to form lead-2 sulfate and hydrogen gas. During these processes, electrons are amassed at the negative plate, while positive charges develop at the anode because of the deficiency of electrons. This generates an electromotive force between the anode and the cathode. A single cell has an EMF of 2.2 volts when fully charged, but this drops to 2.0 volts when it is working. As the battery continues working, a white deposit of lead-2 sulfate forms on the plates and the relative density of the electrolyte drops because of the formation of water. In recharging, a direct current is passed through the cell in the opposite direction to that during discharging. The process that takes place during discharging is reversed during recharging.